Hey, Davi.
Hey there, can you hear me?
Yeah, I can hear you. Can you hear me?
Yeah, I can hear you too.
That's good. That's good. Yeah,
How are you doing?
I'm doing fine. A little bit tired, but I just took a nap earlier, and now I'm feeling more rested.
Nice, I guess. I just
Yeah,
woke up to attend this. This is the normal stuff.
yeah. Did you just wake up from a nap too at Brazil?
What?
Did you just wake up from a nap too?
Yeah.
I see. But what time did you sleep?
I slept at 10 p.m.
10 p.m. and you set alarm for what time to wake up?
At le- I don't know the name of the time in English, but I think it was midnight at 5. Forgot what I'm gonna
Oh,
say.
midnight.
Yeah,
Oh, so
I
like
said
1 hour
that.
ago for you?
Yeah, it was about 10 minutes ago.
Oh, 10 minutes ago, about 10 minutes ago. Oh, shoot. So midnight for you is 1 a.m. or is midnight for you
Yeah,
12 a.m.?
yeah, it's midnight right now. So it's gonna be 1 a.m. 2 minutes.
I see. Yeah, see. What other languages do you speak?
I don't speak English and Portuguese, to be honest.
Oh, English and Portuguese.
Yeah,
I
Portuguese
see.
my home language. No, I'm from Brazil, so of course I have to speak Portuguese.
Yeah,
Duh.
yeah, yeah. Okay, can you say my name is Davi in Portuguese?
My name is Davi.
Oh, that's in Portuguese?
No, 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 no. Meu nome é Davi. That's my name in Portuguese. That's how you
Oh,
say.
oh, wow.
Meu nome é Davi. It's how you say it in Portuguese.
Mm-hmm. Dang, Davi.
Yes.
I see. Yeah, I think people are gonna show up later in like a few minutes. So you could listen in, learn,
All
and
right.
watch. Yeah,
All
because
right.
you I think you're gonna take organic chemistry soon, like well, in sometime in college maybe. Yeah,
Yeah,
when
for
you go to
you.
college, right? And
Yeah.
when you take that class, you're gonna have a head start because you're already getting here early, learning, seeing things, and then once you get there, you're gonna be like, oh, I see that before. I see that before. I know what's going on.
Yeah, because I've attended your work office hours. Yeah.
Yeah.
Yeah. So I
Right.
have a head start once I reach there.
Yeah. And well, once like everyone like doesn't show up to these office hours anymore, you and Ryan could ask general chemistry or AP chemistry questions, and then we could like start at the beginning too, like start
Yeah,
learning
for
from the
you.
beginning too. Yeah, uh, that's good.
Yeah.
Do you like watching football?
No, I don't really like sports, to be honest. Only sport I
Oh,
like is swimming. I like swimming.
oh, you like swimming?
Yeah.
Uh-huh. That's good. Did you watch
Yeah.
the Olympics?
I watched it a little bit. My country won like the volleyball.
Oh, volleyball,
Yeah, my country got first place in
gold.
volleyball
That's good.
globally.
Yeah.
Got gold medal.
Uh-huh.
So yeah.
That's good. That's good.
Yeah, for you. Okay, there's one now.
Uh-huh.
Silence.
Hey, Alessandra. Yeah, so today we can go over um the NMR worksheet that you sent me. I haven't looked at the key for these yet, so I don't know what the correct answer is, but then I could like walk you through my thought process on how I think about these problems here. And then we could double check at the end if I get it right or not. But we'll see. We'll see here. I don't know if I'll get these right, but I'll let you know my thought process on these problems. Okay. So the general guidelines. Let's see. There you go. For these spectroscopy problems, I follow these 5 steps, right? And generally in the order, but people do spectroscopy problems in different ways. But this is like my thought process on how I approach it. Right. So the first thing I always do is I always calculate the degrees of unsaturation, or DOU, and the equation for that is going to be 2C plus 2 minus H minus X plus N all over 2, right? Where C is going to represent carbon, H is hydrogen, X is halogen, N is nitrogen. The next thing I look out for is the major IR peaks to show what kind of functional groups are present in the structure, right? And then the third thing I look out for is the H NMR to look at the specific fragments, right? Based on all of the information that it has, how deshielded the peak is, how many neighbors a peak has, and also the integration of the hydrogens, right? To see if we have a ring or a plane of symmetry somewhere, right? There's a lot of information for this HNMR, which is why HNMR is going to be like very important for spectroscopy, right? Because it allows us to predict for the hyperspecific structure because of those subpeaks, which represents the specific neighbors of each peak, right? And then the next thing I do is I connect the pieces together, or the fragments together. Let's call it fragments to keep it consistent. Connect the fragments and pray. Right. Pray, you get the correct structure. But you get most of the points from these 3 steps here: getting the DOU, getting the functional groups present from the IR, and getting the correct fragments of the specific structure. Once you get all of those specific structures, DOU and functional groups, then you try to connect those fragments together to get the specific structure, right? And then the fifth and last thing I do is I verify with a lot of information that we have, right? A lot of sources of information. You verify with the chemical formula. That's the first thing I look at, the chemical formula, to see how many carbons I used up, how many hydrogens I used up, and how many heteroatoms I used up, like how many halogens, oxygens, nitrogens, if any, right? And that will help guide me through what else is in the molecule, right? Because if I tried drawing like random structures in the molecule, I was like, what? Am I almost done, or is there more carbons to be accounted for, right? And that's where the chemical formula comes in, because once you start guessing, you count how many carbons you have, and then you subtract that from how many carbons there are in the chemical formula, and then that's how many carbons you have left, and then you can just start guessing from there, and then see if everything else makes sense. Right? And I'll show you what that means when I do a concrete example. Right? Verify with the chemical formula, the degrees of unsaturation, the IR functional groups, the HNMR, and you could also verify with, let's say, um, functional groups, DOU, IR, HNMR. Yeah, that's it. Right. Okay, so what compound do you guys want me to try on first? Because I don't know any of these compounds. I haven't looked at the key yet, but I could work on this for you guys. But which compound do you guys want me to try for you guys first? And we're gonna follow these general guidelines here.
Can you just start with the first one?
The first one, okay, yeah. So let's go do compound A, C15H20O2. So when we calculate the DOU, that's 2 times 15 plus 2 minus 20. Okay. There's no halogen. There's no nitrogen. Oxygen is not included in the formula. So we're going to do all over 2. 2 times 15 is 30. 30 plus 2 is 32. 32 minus 20 is 12. 12 divided by 2 is 6. Right? Now, automatically, I see this DOU is more than 4. Right? And if it's more than 4, I'm going to assume that a structure most likely has a benzene ring. Right? Because this benzene ring here has 4 degrees of unsaturation. 1, 2, 3 double bonds and a ring. 3 plus 1, 4. Right? And to verify that we do have a benzene ring, I know that benzene hydrogens, like the hydrogens directly attached to the benzene, is going to be between 6 to 8 on the HNMR. Right? Which we do see here, 6 to 8 on the HNMR. So our structure is going to have a benzene. And there are benzylic patterns to show you if your benzene is either ortho, meta, or para. If your benzene is disubstituted. Have you guys yeah, I don't think 118B, you guys don't go over benzene, ortho, meta, para stuff yet, right? But I think there was a lab which had the ortho, meta, para, benzene, HNMR things, right? Like have you guys done that lab, or did they change it up and made you guys do the lab later in the quarter or session, summer session, right?
I don't think so, but I'm not sure.
Okay. So yeah, because usually like previously this 118B quarters, they make you guys do a warm up spectroscopy worksheet, which that worksheet has benzene structures on it with ortho meta para patterns. But you guys learn more about that in the middle of the 118B, right? So since you guys haven't seen that, let me go over the benzene patterns with you guys. Right? A disubstituted benzene. Right? Substituted benzene. HNMR patterns. Right? And this is gonna help you determine where the two groups are going to be located at. Right? So let's say we have a benzene right here, and it's disubstituted, meaning that it has 2 R groups attached to the benzene ring. I'm gonna label it as R and R prime to show that they are different groups of each other. Right? This is disubstituted because there's 2 groups like that. If you see that the 2 groups are right next to each other, like there's no gap between them, there's no carbon separating them, that is specifically called the ortho position, right? This R prime is ortho to this R group. Ortho meaning that it's 1 carbon away, right? Let me actually draw that out here to make it a clearer reference, right? Because let's say this is an R group. The ortho carbon, I'm going to abbreviate that as O, is 1 carbon away from the reference carbon. This is going to be our reference carbon here. The meta carbon is going to be 2 carbons away. Para carbon is parallel to it or on the opposite side of it, right? So O is going to represent ortho, M is going to represent meta, P is going to represent para. These are just position terms to show what carbon are we referring to, right? These carbons here are not always ortho. These carbons here are not always meta. This carbon here is not always para in this orientation, right? Because you can have a benzene ring where, let's say, your R group is not at the top, but it's some at a weird carbon like this, right? Now the ortho carbons would be these carbons, the meta carbons would be these carbons, and the para carbon would be that carbon right there, right? Because these are relative positions based on the reference point, right? Our reference point on the right side is this carbon right here, and ortho is 1 away from the reference point. Meta is 2 carbons away from the reference point, and para is the furthest away, 3 carbons away, or parallel from it, across from the reference point, right? So those are ortho, meta, para terms, right? So let's talk about di-substituted benzene rings, meaning there's 2 groups of each other on the benzene ring, right? Where they could either be ortho, meta, or para to each other. In this first example I give you guys, they are ortho to each other, right? Because they're 1 away. Okay. So now let's see. I'm gonna draw out the hydrogens directly attached to the benzene right here, right? These hydrogens directly attached to the benzene is going to show up between 6 to 9. You most likely 6 to 8, right? But it could go up to 9, 6 to 9, right? Okay, so there is no planar symmetry here because these are 2 different R groups, right? If they are the same R groups, there would be planar symmetry, but there's no planar symmetry here because they are unique R groups. And because there's no planar symmetry, all of these hydrogens are going to be unique, right? Let's call this HA, HB, HC, HD. Let's focus on HA. HA is going to have 1 neighbor, which is HB. And because it has 1 neighbor, it's going to have a doublet, right? And let's call that HA. And there's 1 HA. HB is going to be a triplet because it has 2 neighbors. HC is going to have 2 neighbors, so it's also going to be a triplet. HC, and there's only 1 HC. And HD is going to be a doublet because there's only 1 neighbor, right? So at the 6 to 8 range of the HNMR, if you see this pattern right here, then you know that your benzene is ortho, right? Ortho is going to be the hardest one to recognize because it has all these weird subpeaks here, peaks here, right? Just think of it as like 2 triplets and 2 doublets. If you see 2 triplets and 2 doublets on 6 to 8, then you know you have a benzene ortho, ortho benzene ring, right? Let me put that down. 2 doublet, 2 triplets. If you see that, then your benzene is going to have 2 R groups that are ortho to each other, right? Now, meta is a little bit easier to recognize because it has this distinguishing peak to it, right? And I'll show you what that peak is, right? So this is going to be an example of a meta benzene ring where the 2 R groups are meta to each other. There is a 1 carbon separation between them. I'm going to do the same thing, draw out the hydrogen explicitly, label them A, B, C, D. No planar symmetry, so all of those hydrogens are unique, right? Since they are on the benzene, they are going to be between 6 to 8. Right. HA is going to be the distinguishing feature, distinguishing peak on the meta benzene, right? Because HA has 0 neighbors. That's not a neighbor. That's not a neighbor because that's not hydrogen. So that is going to show you a singlet. If you see singlet, then you know that you're going to have a meta benzene ring, right? Well, that's HA, one of them. HB is going to be a doublet. HC is going to be a triplet. And then HD is going to be a doublet, right? Because HD has 1 neighbor, HC has 2 neighbors, HB has 1 neighbor. And then the number of suffix represents the number of neighbors plus 1, n plus 1, right? These numbers here just represent the integration. How many hydrogens represent this peak? And it's 1 of each only, right? Because there's no planar symmetry. Right. So let me put this down so that you guys don't get confused with the thing on top. Okay. Let me make a line here actually to separate them. Right? Yeah. See this is a singlet. Then you know that your benzene is di-substituted and has a meta. Right? It has to have these other peaks as well to make it di-substituted. Right? Okay, now the last one, para, is the easiest one to recognize. Right? So let's say our two R groups are anti to each other, opposite from each other. These are para to each other as well because there's like, yeah, they are para to each other, right? Because they're like 3 carbons away from each other. Okay, let's do the same thing. Explicitly draw out all the hydrogens of the benzene, which are going to be between 6 to 8, right? But now there is a plane symmetry, right? The plane symmetry is not going to be here because these are 2 different R groups, 2 different unique groups. The plane symmetry is going to be down this middle right here, right? Imagine this was like some kind of group. You're cutting that group in half from a left and right side, right? You can think of it as like the mid sagittal plane, right? Where you cut it between the uh, left and right side, right? Where everything on the left side is everything is the same as everything on the right side, right? If this was like, let's say an alcohol, you're cutting both the oxygen and hydrogen in half, where this is the left side of the oxygen and hydrogen, this is the right side of the oxygen and hydrogen. That's the plane of symmetry. Not this right here, not the transverse plane, or horizontal plane, right? It's gonna be vertical here. On how I drew it, right? There could be a benzene ring where the para groups are like that, right? Now the plane of symmetry is at an angle like that, right? So it's just dependent on where the R groups are aligned. Right? But the way I drew it here, the R groups are aligned vertically, and that's where the plane of symmetry is, right? And because of that plane of symmetry, these are symmetrical hydrogens, HA, and these are symmetrical hydrogens, HB. Right? So now, if we draw that on the H&MR scale, 6 to 8, HA, look at one of them. Let's look at this one. That one only has one neighbor, HB, which is going to show up as a doublet. HB is also going to show up as a doublet, one neighbor. Let's just say this is HA, this is HB, but there's going to be two of them. So you're going to see the number 2, right? Because there's 2 HA hydrogens and there's 2 HB hydrogens, right? HA has one neighbor, doublet. HB has one neighbor, doublet. Right. So that's why if this is the easiest to recognize. If you see 2 doublets like this, then that's a para benzene, especially when you have 2 and 2, right? And notice how all of these H&MR, they add up to 4, right? Because that's going to be 4 hydrogens, 4 remaining benzene hydrogens if you have 2 R groups, right? 2 R groups, that means there's 4 spots left for the hydrogens, 4 spots left for the hydrogens, right? 1, 2, 3, 4, 1, 2, 3, 4, 2, 4, right? 4 benzene hydrogens, which means that there are 2 R groups, which means that those 2 R groups can either be ortho to each other, meta to each other, and para to each other. And then we could tell that by looking at this pattern at the 6 to 8 range and the H&MR. Right. And then you'll get back to this more midterm 2, after their first midterm. Right. So looking at this here, we see that we have a singlet, and these hydrogens here at the 6 to 8 range, the benzene range, add up to 4. So we know that we have a meta benzene, right? Because at the meta benzene, we have a singlet, right? These peaks right here, they don't have to be in this order, right? They can be flip-flopped around, right? The singlet can be here, it can be here, it can be here. Like, it doesn't matter, right? As long as there's a singlet between 6 to 8, which in this case, there is a singlet between 6 to 8, which is that singlet. So we know that we have some kind of meta benzene like this, right? I'm drawing this squiggly line to show that that's a fragment. I don't know what's attached there yet, but I do know that our structure is going to be meta benzene, right? So far. Okay, this is right here at the bottom as a CNMR. I didn't put that in my general guidelines, but some people do use it, right? So if you think that using the CNMR will help you predict your product, then use it. But I like using the IR instead because CNMR is just also what functional groups are present. It could be useful in the 118C at the beginning, but for now, I'm gonna ignore it. We don't need to. We don't need it to predict the structure, right? So I'm just gonna cross that cross that out. Okay, so now let's look at the 4 to 6 range. The 4 to 6 range is the alkene range on HNMR, right? And then we see that we have HA and HB. So I'm going to draw an alkene right here. And then we can't read the number of neighbors here because there's complex splitting there, right? So to tell what kind of alkene we have, cis, trans, geminal, we got to look at the J values, right? So these are the J values here. Think of it as a matching game. Let's see. Typical J values, and then the relationship between the hydrogens that are matching, that have matching J values, right? Around, it doesn't have to be exactly this number. It could be plus or 1, right? 2, these are the important ones. Around 2, around 7, around 10, around 16. Around 2 is the geminal. Around 7 is the allylic. Around 10 is the cis. Around 16 is the trans, right? Okay, so let's see what's matching here. We see HA and HB. Oh, yeah. They have a matching J value of 3, which is around 2. So that means that they are going to be geminal to each other, right? So we do have a HC as well, which is HC over here. And then if you see HC is not between 4 to 6, right? That means that HC is not on the alkene, right? Because the alkene hydrogens, the ones directly on the alkene carbon, is going to show up between 4 to 6. HC right here is most likely going to be an allylic hydrogen, right? And allylic, what that means is like, it's a position term, right? The carbons directly on the alkene is the vinylic position. The carbons away from the alkene are called the allylic position, right? You could also call that the alpha carbon, right? And then it does show up between the alpha region, which we said was between 2 to 3, right? Which means that those hydrogens are alpha to an alkene, alpha to a carbonyl, alpha to something, right? Okay, so let's see. HC and HA has a matching J value of 2, which is geminal as well. So I'm getting confused here because like there's 2 geminal. What the heck? And then HB and HC has matching J value of 1. And there's 3 HCs. And there's 1 HAHB. Okay, I'm gonna guess. This is what I'm guessing. That this is HA, this is HB, right? They are directly on that alkene right there. And then we do have an HC. Let's see, what could this be? Let's see. Alkene. there's one HA, one HB. They're not cis to each other, HA and HB, because they don't have J values of around 10. They're not trans because they don't have J values of 16. They do have 3 and 3. Geminal. Hmm. HC is not 46, so it's not directly on the benzene. Right. So that's it. Could that be it? No. There's 3 of them. Huh. Okay, I'll get back to that. I'll get back to this alkene stuff. Wait, I'm gonna look at the other things first. Let's look at the IR. Right, IR 3100. That's the sp2 carbon hydrogen peak. 3000 around that range is the normal sp3 carbon hydrogen, so we can ignore that. 2950. That could show an aldehyde, right? We can have an aldehyde. Right. And to make sure that we have an aldehyde, this aldehyde hydrogen here is going to show up around 10 on the HNMR, right? But we don't have that peak at around 10, so we're not going to have an aldehyde. Right. 1680 is going to show our carbonyl, right? An oxygen that is bonded to a carbon, right? So we're going to have a carbonyl somewhere, right? And our carbonyl here, I'm going to guess is an ester because we have 2 oxygens. One oxygen is going to be the carbonyl oxygen. The other oxygen is going to be the oxygen of the ester, like that, right? So I'm going to guess that that's our thing right there. 1610, that's the alkene right there. So that's where our 6 DOUs are coming from, right? 4 from the benzene ring, and the other 2 are coming from these double bonds here. This is 1 DOU, the double bond between the carbon and oxygen, and then this is the other DOU, the double bond between carbon and carbon. That's 2 plus 4, 6. So that accounts for all of the DOUs, right? Anything like 1500 below, fingerprint region. So I'm just gonna ignore these peaks, right? Okay. So 3 to 4 range on the HNMR is the electronegative, highly electronegative atom range. Right. So I'm gonna say that because we have an ester, I'm gonna say that those 3 hydrogens right here with 0 neighbors are these 3 hydrogens right here. I'm gonna like circle that pink to show that those pink hydrogens are these pink hydrogens here, right? And because these pink hydrogens are next to an electronegative atom oxygen, that's why it's going to show up between the 3 to 4 range on the HNMR, right? And we see that these pink hydrogens here has 0 neighbors, right? Because if we go 1, 2, we hit an oxygen, right? We can't go further than that. Like that's gonna block it having neighbors, right? So even if we do go 3 right here, right? That's a carbon. That's not a hydrogen. So that's not this peak right here. It's gonna have 0 neighbors, which is gonna show up as a singlet, right? And even if this oxygen does have a hydrogen, this hydrogen does not count. 1, 2, 3, because the hydrogen has to be on the carbon to be considered a neighbor. To be considered a neighbor, the hydrogen has to be on a carbon, right? So this is what I have so far. This peak right here, this ester, with the OR being a methyl group, right? Methoxy group. Okay. Now let's move on to this alpha region. Okay. Let's see. we do have two hydrogens that have, let's say, two neighbors, because both of these two hydrogens are triplets. So they have two neighbors each, two neighbors, two neighbors. This hydrogen here has 1, 2, 3, 4, 5, 4 neighbors. This hydrogen here, this set of hydrogens here has 1, 2, 3, 4, 5, also 4 neighbors. So this is a big molecule. Big molecule. 4 neighbors, 4 neighbors. Okay, let's see. Now this is where I start guessing here, right? But the 2 to 3 range, we know that's the alpha region. So we know that these two hydrogens here is going to be alpha to something. Alpha to either the alkene or alpha to either the carbonyl here, right? So I'm going to start guessing here. Let's see. Start guessing and praying. Oh my gosh, let's see. Okay, 2 hydrogens. See, do we have 2 hydrogens? Oh yeah, we do. Okay. Boom. Okay. So I'm guessing that one of the fragments of the benzene is this right here, right? Where I'm gonna circle the peaks. I think what it is, right? I think those 2 purple hydrogens are gonna be these 2 purple hydrogens here with 2 neighbors, right? Which its 2 neighbors are here, and it's alpha to the alkene, which is why it's gonna be between 2 to 3, right? And then I'm gonna circle the other alpha peak green to represent these green hydrogens here, which has 2 neighbors as well, which are these 2 neighbors, and it's alpha to the carbonyl, which is why it's showing up between 2 to 3 on HNMR, right? Oh, we don't have that there. It's supposed to be methyl group CH3 like that, right? Okay, let's see how many carbons we used up so far. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? We used up 10 carbons, so we have 5 more carbons to use up. We already used up our oxygens. Okay. Now, we do have an alkene, and I'm guessing it's a terminal alkene, right? Because of this geminal thing. And if we have a geminal alkene, then that's usually a sign of a terminal alkene, which means that the alkene is at the end of the molecule, right? So I'm just gonna go right here. 1, 2, 3, 4, 5. Right, and let's see if this works. Wait, no, but then HC has 3 hydrogens. 3 hydrogens. So how can I account for that? Wait, how many hydrogens? This is so weird. What if we... No. Because that would be cis. This would be trans. Okay, the alkene is messing me up here. What the heck is going on here? Dude, okay, 4 neighbors, 4 neighbors. Yeah, so that has to be somewhere in the middle. Something like this. Hmm. Is there 2 hydrogens with... No. Ooh, okay. I'm gonna shorten this. I'm gonna shorten this chain. All right, I'm gonna shorten this chain and just make the ester like that. Right. In order for these 2 hydrogens here to be alpha, which are gonna represent those 2 hydrogens right there to be alpha with 2 neighbors, and its 2 neighbors are gonna be right here. Okay. So then, let's see. 2, and I'm gonna say that these 2 hydrogens right here, which I'm gonna circle as, I already used purple, pink, let's use this color. Represent that right there with 4 neighbors, and then its 4 neighbors are going to be here, right? 2, 4. And now let's color code this set of hydrogens, which is going to be red, right? And that red peak is going to represent this red peak with 4 neighbors as well, right? and its 4 neighbors are going to be right there. This is so weird. Like HC with 3 hydrogens. 3 hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Right. I'm just gonna put one more carbon right there and put an alkene right there. All right, let's see. Four neighbors, these 2 hydrogens here. But there has to be, yeah, this is alpha. So the HC here is going to represent this HC here, right? But I don't know how this is 3 hydrogens. Like, let's see what's going on. No. Oh, wait. Let me try something. Okay, wait. Let me get rid of this. Put an ester right here. And then the 2 hydrogens are going to be right here. And then put a methyl group right here. Put an alkene right there. Right. And then the 3 hydrogens of HC are going to be that peak. Right. Which is why the J values of C is 3 hydrogens, which are these 2 hydrogens right here. And they are going to be allylic. Or not allylic. They're going to be long range. That's the other thing about the J values. Long range. Right. Long range, which is 2. Right? Because the other thing that is close to 2 is going to be long range. Let me see. Gemino, and let me put 1 here as well. Okay, let me go down. Okay, around 1, the relationship between the 2 hydrogens are going to be long range, right? Because this is going to be HA and HB, which we know are geminal to each other, because HA and HB has a J value of 3, right? Let me actually put geminal as 3 to show that it's higher, and then long range as around 2, right? Because these are like ballpark ranges. Geminal and long range are very similar to each other in that they're very close to each other. But geminal is going to be higher than long range, right? Where we see C and A are going to be long range, which means that HA and HB right here. Let's see. Have these HCs long range. It's not allylic, right? Because to be allylic, this carbon here is the allylic carbon, right? And let's say this was a hydrogen, then that would be allylic, right? It has to come off of the same carbon. But because this carbon is far away, too far away, it's not allylic to that set, right? Right. This is the this carbon here is allylic to this alkene carbon, right? This carbon right here that I'm like dotting is not allylic to this carbon, right? That's too far away. We call that long range because it's far away, right? Okay, so did I use purple? No, yeah, I used purple already. What was the other one? Red. No, I used red in that. What's this then? Oh, okay, yeah. So that's gonna be purple now because I got rid of the purple hydrogens here, right? So now this is purple. The 2 hydrogens that are allylic to this carbon, which is why it's between the 2 to 3 range and has 2 neighbors, which is gonna show up as a triplet right here, right? So this one is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 carbons. 15 carbons. 2 oxygens we used up, and there were 20 hydrogens in the chemical formula. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, so I'm going for this as my final answer. I'm going to redraw it so then nothing gets in the way. Right, but we'll check if this is right. Okay. Is this the right structure? 6 DOU, 4, 5, 6 DOU. We have a carbonyl, we have an alkene, we have a benzene. And it's meta benzene as well. Yeah. So when I tried this problem, I got the first attempt wrong, and then I kept looking at the peaks and then just tried something random, and then it turned out to be okay, maybe, if this is right.
How much do they care if you get the structure right or wrong?
At most it's gonna be two or 3 points, right? You get
Okay.
most of the points because spectroscopy is gonna be like 10 to like 12 points, something like that, most likely 10. You get
Okay.
majority of it, like eight of it at least, by getting the DOU, the fragments like I did here, the metabenzene, the ester, and then if you do like what I did here, right, which
Yeah.
is gonna represent something like this, the alkene as well, like fragment, like instead of getting that piece together, if you do something like this, then you get partial credit for that as well. That's how you get majority of the points, right? This is just like the cherry on top.
Okay.
Yeah. Wait. So I recommend only doing this only if you have time at the end of the exam, right? Focus on everything else like vocab, predict the product, mechanism, all those other questions first, and then H&MR, get the fragments done, and then move on to the rest of the exam, right? And then once you have more time, which is a rare thing in Lehman's exams, then you can try getting that structure. Right. But is this correct? Is this correct?
I sent you the answer key. I messaged it.
Oh, sure. Yeah. Let me go get my phone really quick. I'll be
Okay.
right back. Okay, let's see. Let's check it. Oh shoot, yeah. Thank you, Amrita and Alessandra. Okay, let's see. Okay, so no, this is not correct. Oops. The correct structure. Let's see. Let's analyze it too. Like why this is wrong. Let's see. And compare the difference between what I put and the key. Okay. Red. Ether. And then meta, right? You get partial credit for that. This is a meta benzene as well. 1, 2, 3, 4, 2, 3, 4. And this fragment here was the fragment that I put right here. So we get partial credit for that as well. Partial credit for the meta benzene. Partial credit for the carbonyl, carbon of 1 oxygen, which is right here. And then we had a geminoalkene, right? Geminoalkene, and I knew we had a geminoalkene. Like I was like, oh, this is gemino, so we get partial credit for the geminoalkene as well, right? It's just like connecting the pieces together to the specific structure, right? We got the parts of it, but we put the parts together incorrectly. Let's see what's the difference though. Yeah. This methyl group here has 0 neighbors. Methyl group here has 0 neighbors. 2 hydrogens are geminal. 2 hydrogens are geminal. 3 hydrogens here that are extremely deheated between the 3 to 4 because they are next to that oxygen, which are
represented by these three hydrogens here. And then, yep, 2, 4, 2, 6, 8, 2, 4, 6, 8. So for Levin's spectroscopy problems, right, since she tends to use big chemical formula molecules, I do know some 2Ts who asked me, would this work instead of the key, right? And then I told them to ask Levin's during office hours, and she does accept some molecules that are not part of the key, right? As long as it works out and checks out with all the information that we did, like the IR, HNMR, J values, and then nothing else interferes with it, right? We've got the meta benzene ring as well. Then she accepts some molecules that are not part of the key. So I recommend going to Levin's office hours and then asking her if this structure would work for compound A as well, right? I'm actually kind of curious, like like if she accepts this as the answer, right? Because I know previously some 2Ts got a different structure that got full credit without being the key, right? Because the only differences here are like the arrangement of these structures here, right? We got 6 DOUs, 4, 5, 6. Yeah. Right. Are her office hours on Zoom or in person?
I think she does both.
She does both. Okay.
Yeah.
Dang. Cute. Yeah, but the thought process of how I got the fragments makes sense, and like this benzene pattern makes sense. Yeah.
Yeah, it makes sense. Thank
That's
you.
good. That's good. Yeah. Okay.
Can we go over like the second example? I think it looks like way easier, but
Yeah, this one right here. Yeah.
Yeah.
Let's do it. No oxygens, no electronegative atoms, just carbons and hydrogens. Okay, let's do it. I'm okay. Here's what I'm gonna do. I'm gonna try to do it without explaining, and then you guys can watch me to do it. And at the end, you guys can ask me questions if you guys like get confused on what I did.
okay.
Okay. Let's do that. Wait. H is 16. 18 plus 2 is 20. 20 minus 16 is 4. 4 divided by 2 is 2. Okay. That's 1. Wait. 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 20. Okay, alkene, let's put alkene random. There. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Right. That's still more hydrogens than what it is. So I'm guessing we have a ring somewhere because we used up 1 DOU for the alkene, right? Which is going to represent this alkene peak at 1600 IR. 3000, 2900, that's the regular sp3 carbon to hydrogen bond. But let's see what the ring size is. Ring size, let's see. H, A, B, C, D, E. Okay. Let's look at the alkene. 18, 18, matching. HA and HB are trans to each other. Let's say this is HA. This is going to be HB, right? Trans. All of this. Eight and 8. Cis? Say, I guess. Cis. allylic. D and A, allylic. Wait, if this is allylic, then that has to not be a hydrogen. Seven. No, nothing matching with 7. 1, 1, 1, 2, 2, 2. Nothing matching with 3. Oh, no, that's hydrogens. Okay, there's 3 dihydrogens. Those 3 dihydrogens are gonna be allylic to HA. So let's say those dihydrogens are these 3 dihydrogens here. And let's see. Yep, they are alpha. Right? These 3 dihydrogens are alpha to the alkene. C and B are matching, and they're matching 8. Okay, I'm just gonna ignore that and see if it works. We'll see, we'll see. And then this has to connect with something to it. Okay, that's my alkene fragment right now so far. Okay. So that's 1 DOU. Oh, okay, we also have HC, which is 2 H's, right? HC, 2 H's, and I'm gonna show that those 2 HCs are these HCs right here, right? And it's also alpha because it's 2 to 3 range, right? And then because there's 2 HC hydrogens, those are the 2 HC hydrogens right there, right? We have A, B, C, and D, right? And that's the fragment right there. Okay. So far my alkene fragment is this. Boom. Like that. Trans alkene with a CH3 coming off at the end of it, and then CH2 connecting to some kind of group. I don't know yet. Right? And that used up 1, 2, 3, 4 carbons, which means that we have 5 carbons left. And I'm automatically just gonna put that 5 carbon as a ring, right? Like this. Wait. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, this looks weird, but we'll double check. Especially this 1 hydrogen here that has 1, 2, 3, 4, 5, 6 neighbors. So that 1 hydrogen should have a multiplet that has 7 subpeaks. Okay, so we don't have that. So it's not this here. But we do have a 1 hydrogen that has 1, 2, 3, 4, 5, 4 neighbors. 4 neighbors. Okay. Let's see how we can make this happen. 1 hydrogen with 4 neighbors. Okay. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 hydrogens. Yeah, that's good. But this does not satisfy the HNMR because this one H should have 7, but it doesn't. So let's see what can we do. Yeah, let's get rid of that. Yeah, we already used up HA, used up HB, used up HC and D. Now it's just this one H. This one H right here. Right. One H with 4 neighbors. What if I no that's not gonna work. 1 hydrogen. Restrict this to 4 neighbors. I can't add another double bond. Like that. Because that's gonna be 3 DOUs. And that's gonna be less hydrogens. Okay, restart. alkene. Get the alkene right. 2 C's, alpha, 8, 8, B, right? This is going to be allylic to each other. Oh, yeah, okay. The 8 of the C and the 8 of the B match to show that they are allylic to each other. The 6 of the D and the 6 of the A are matching to each other to show that they are allylic to each other. The A and B match J values of 18 to show that they're trans to each other. So I'm leaning towards this fragment right here, which is this fragment. D, A, B, C. 1, 2, 3, 4. 5 more carbons. Ring. 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 Oh wait, but we don't have 2 hydrogen. This will not work because these 2 hydrogens here, like there's no peak for 2 hydrogens. So what is going on here? There's something weird going on. What is this? This is so cursed. This, is it symmetrical? No, it can't be. Oh, wait, it might be. Let's see. Let's do this. There you go. So hope it's symmetrical. Plane of symmetry down here.
Yeah, that's what they have on the answer key.
Oh, okay. Let's go. No ring. Okay. Oh my god. Because if I did put a ring, we would have had to have a peak that represents 2 hydrogens, but we had no peak that represents 2 hydrogens, right? Okay. Yeah. It's good because let's see, how can I label this? These H's here are HD from the J values. They already labeled it for us, HD. Right. These hydrogens here are HA because HA and HD are allylic to each other because they have matching J value of 6. These green
Wait,
hydrogens here.
sorry, don't they also have the matching J value of 2?
HA and HD.
Yeah.
Yes, they do, but we just look at the important ones. We look at the more the more, how do I say this? The one that gives us a more distinguishable relationship.
Okay.
Right. Because these hydrogens here will have random J values as well, but we look at the biggest ones because they're the most prominent ones that show up, which is gonna mean that they have a most likely relationship with those G values associated with those bigger J values.
Okay.
So we look at the bigger J values of all these hydrogens. Right. And this is HB, and then HC is allylic to HB, which are these HCs right here. It is 2 of them. HC, and this weird looking 1H with 4 neighbors. Let's give that the color of this. Right. Let's erase that blue. There's that H right there, right? And that's considered 1 because of the plane of symmetry here, right? That's why we don't see 4 C hydrogens. We don't see 6 D hydrogens. We don't see 2 B hydrogens. We don't see 2 A hydrogens. We don't see 2 of these hydrogens because the plane of symmetry simplifies it down into like divide by 2 into half. Right. But you guys saw how I like messed up the first time, like by saying there's a ring, because what I did first was make it saturated 9 carbons to see how many hydrogens there are. That's way too many hydrogens, so I give it a double bond. That did reduce the number of hydrogens, but not enough to get 16. And then I guessed that there's gonna be a ring somewhere to get the right number of hydrogens. But this ring right here was a problem because it would have peaks that are not on the HNMR, right? So there is gonna be a plane of symmetry somewhere, right? And the more practice,
you guys do the more patterns, you guys are gonna recognize and see. And what are the tricky ones like rings, symmetry, carbonyls, esters, ethers, and the guess is gonna be like better. There's like a lot of trial and error, right?
Thank you.
Yeah, no problem. I hope this helped like showing you guys my thought process of how
Yeah,
I,
it did. It did. Yeah.
yeah, that's good. That's good. No problem, guys. See you guys next time, maybe tomorrow or during our office hour. I mean our private sessions. Yeah.
Thank you.
Bye.
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 Bye there.
Bye, Davi. Did you learn something new today? But this like there's a lot of information that you haven't learned yet because it's
Yeah,
like
for the didn't learn all of that yet.
yeah, right.
Yeah, more complex stuff that the other awesome students that have learned before, right?
Uh-huh. Right. They learned
And
about the
that's
background information already, so they just gotta know how to approach these kind of problems. But they really learned about the
yeah,
background.
true.
Yeah.
Yeah.
Hey Ryan.
Hello.
Hey. Oh
So
yeah. Wait, I forgot to do my push-ups. What
I
is
was
wait,
gonna
what
remind you.
is
6.
day 6, right?
Yeah.
Yeah, day 6. Let me do them right now.
Mhm.
6 push-ups.
It's consistency. You'll
Yeah.
get stronger every day.
1, 2, 3, 4, 5, 6. Yep.
All right.
Good.
Also, tomorrow is like my last free day before I have to go back to school on the 15th.
Oh shoot. Dang. You gotta enjoy all you can, and rest and
Rest. Yeah.
plan for the thing.
Yeah.
Right. Oh, that was good. I always feel good after doing push-ups or exercising because the pump, more blood flow. I can think more clearly. Right. Do you do exercise, Davi?
I don't. I don't do exercise to eat. I don't eat a lot, to be honest.
Yeah, I see.
My mom works at Costco, so she buys all the yogurt, all the milk, and all the eggs that like if we finish it, she just buys more. Like it's no problem.
Right.
Nice.
I see.
I'm like the luckiest person.
Right. Okay, so I do have another session at 10, but we can talk more when I don't have a session. But it was
True.
nice catching up with you guys, Davi and
Yeah,
Ryan.
for you. For
Yeah.
you.
All right.
Okay. Yeah, I'll see you
Yeah.
guys. Bye.
I'll see you
Bye.
guys.
I see you
Bye.
Bye-bye.
tomorrow.
See you tomorrow. Good night. Good night.
Good
Yeah,
night.
good night.
Good night. Okay. Hey Katya, let's rejoin this session for the recording to process.
Okay.
Okay.